Hello everyone, my name is Daniel Downing and this is my flight presentation for Running Rough. So quickly we'll go over what VMC is. So VMC is the speed below which aircraft control cannot be maintained if the critical engine fails under a specific set of circumstances. So on the airspeed indicator, it's marked by the red radial line for most multi-engine aircraft, which we can see. And the blue line on the airspeed indicator is the best single engine rate of climb, or VYSE. Which is represented by the blue radial line, which we can see on the airspeed indicator. So VYSE is the airspeed to pitch for in an engine failure emergency to provide the aircraft with some amount of climb performance depending on the altitude. So some of the various factors that affect VMC, we can use the mnemonic SMAC-FUM, which is what my instructor taught me. So basically, when it comes to VMC, anything that has an increase in performance is going to increase VMC. So the first one we can see on a standard day, it's going to increase the performance of the aircraft. Obviously, on a standard day, the air is going to be more dense than if it was hotter. So this is going to increase VMC. Another example, the second one, max power in the operating engine is going to increase performance. It's going to increase VMC. So in the case of this single engine emergency, it's really important to methodically identify the dead engine or the one that's now inoperative and immediately begin pulling the power back on that engine that's still operating at full power, because it's going to increase our VMC. Moving down, we can see the C is representing the critical engine windmilling. If the engine's windmilling instead of being feathered properly, which would be done in the appropriate checklist, we're going to be creating a lot more drag on that dead engine. And then lastly, the most unfavorable weight is going to be light. Again, that's going to increase the performance of the airplane, which is going to increase VMC. So anytime we're increasing VMC, this is bad. So we just want to keep these factors in mind before every flight. And then quickly going over what dead foot, dead engine means. So due to asymmetric thrust, when an engine fails, the airplane will yaw and roll towards the dead engine. The foot not moving to counteract this yawing moment is considered the dead foot, and that foot represents the dead engine. And from there, we can identify and either try to restart the engine or go about securing it per the applicable checklist. So next, we'll kind of talk about some of the factors that are going to be affected when we do lose that engine. So if we don't correct it, we're going to be yawing and rolling towards the dead engine. So if you are not yawed and rolling towards the operative engine, the aircraft will be slipping through the air. Asymmetric thrust not corrected will cause the operative engine to turn the aircraft, and this is going to decrease climb performance, which in a light twin, if we're pitching for VYSE, we need every foot that we can get. A good rule of thumb is to bank 2 or 3 degrees toward the operative engine and a half ball deflection on the turn coordinator. Next, we can review the checklist for an engine failure during takeoff in our Cessna 310. So if it happens while we're still on the runway, obviously we're just going to immediately close the throttle and brake as required. After engine failure after takeoff, we can see some of the things that we would be identifying. So mixtures as required. First, we're going to have to identify the engine that has died, right? So an operative engine, we're going to close the throttle, mixture, idle cutoff, and feather the propeller. Again, we're feathering the propeller to ensure that we're decreasing the drag on that's being created by that propeller. Next, we can see, just like we talked about in the last slide, we're going to establish bank about 5 degrees toward the operative engine. So this is specific to this airplane instead of just the rule of thumb. And next, we're going to be pitching for VYSE, or the best single engine rate of climb, which in our case is going to be 106 knots indicated at sea level, 94 knots at 10,000 feet. And then we can see from there, we're going to be securing the inoperative engine. We're going to be shutting off the fuel pump, the magneto switches, and the alternator on that one, and then landing as soon as practicable. So next, we can see if we have an engine failure during flight, the methodology for identifying and securing the engine is going to be a little bit different. For each phase of flight, if we lose an engine, the process and the checklist is going to be a little bit different for handling the emergency. So the first thing we can see is, before securing the inoperative engine, the checklist is going to have us verify that we haven't just cut off fuel to the engine. We want to make sure that the engine is actually inoperative before we just shut it off. So we've tried all that. If the engine does not start, then we're going to secure the engine. Same thing, throttle, we're going to pull all the way to idle, mixture, idle cutoff, again, feathering the propeller to decrease the drag on that engine. And then moving down, we can see it's similar to after takeoff. And then again, landing as soon as practicable. And then lastly, if we have an engine failure during landing, if we're on final approach and we lose the engine, we're just going to be kind of dealing with it as we're coming down. There's not going to be a whole lot of, we're not going to go through the whole checklist of securing the engine. If we're already on the final approach, we're just going to be landing the airplane as best as we can. In the case if we have to go around, the important thing to note here is that we want to get the landing gear up and we want to get the flaps up if they're extended. If we remember from the SMACFUM, anything that's going to be increasing drag we need to get rid of, because if we're creating drag, we're increasing that VMC, which is bad, because if we reach VMC, we're going to lose control of the aircraft. So in that case, we're getting rid of all the drag, the flaps, the landing gear, the cow flaps, since this airplane's got them, and then establishing best single engine rate of climb, which is going to be the blue line on the airspeed indicator. So for single pilot resource management for this, so SRM is the art of managing all onboard and outside resources available to a pilot before, during flight to ensure a safe outcome. So in this case, we're using our checklist, making sure that we're proficient in the airplane and everything like that. So we need to be able to prepare for all scenarios, including emergencies, before every flight. Engine failures and light twins are especially important to plan for before every flight to make sure that you are proficient to handle this emergency. And next, we'll quickly touch on aeronautical decision making. So ADM is a systematic approach to the mental process used by pilots to consistently determine the best course of action in response to a given set of circumstances. In this case, we're talking about engine failures and light twins. 80% of all accidents are attributed to human error. So in this case, when we're handling this emergency, it's really important for us to slow down, make sure that we're identifying which engine is actually inoperative and that we're not shutting off the wrong engine. There's been plenty of accidents all the way up to commercial ATP pilots that identified the wrong engine being inoperative, and they shut down their one good engine, and then they're just turning into a glider at that point. So in this case, we'd want to use the 5P checklist. This is used to identify decision-making processes of variables throughout the flight. This includes the pilot, the plane, the passengers, the programming, and the plan. So using the 5P checklist in this particular scenario where we're talking about losing an engine, as the pilot, we want to make sure that we're proficient in the airplane, especially when it comes to handling these emergencies. We want to make sure that we're familiar with the checklist that we just went over, handling an engine failure during takeoff, en route, and during landing, because the process for handling that emergency is going to be different for each phase of flight. The plane, it's going to be really important to be familiar with all systems and what to do in the case of an engine failure. Again, reviewing all these things before we go and fly in this airplane. Planning for the best and expecting for the worst. Passengers, we want to use passengers during an emergency if they're comfortable, and especially if they're a pilot. If they're also familiar with this airplane, we can use them to take a little bit of the workload off of us. Next, programming, automation management, use of autopilot, avionics, and aircraft systems. Multi-engine flight is going to require more automation to avoid task saturation. There's going to be a lot more systems installed on the aircraft. And then lastly, the plan. Again, we want to plan for the best, but expect the worst.